I'm not a mining specialist by training. I am a chemical engineer. I work with mining industries managing their energy use. So most of the time we come in and trying to develop a strategy and program to help them reduce their energy footprint, and that's what I do mostly. I'm really excited to be here today, and when Nathan told me that he wanted to talk about energy and innovation and mining, I thought, well, most of the time I talk about the really non-sexy stuff where you go in and replace this equipment, you train the people, you make little step change, little incremental changes to get where you're going to. Those are significant changes once you sum them all up, but they're not really sexy. It's not what people like to talk about. So as much as that's what I do, normally, I'm going to talk about more of the interesting new technologies that may be applicable to the mining sector. They're not all going to be related to the actual mining and processing, but I think they may be interesting to you just to see how they may be related to mining. So just to set the stage a little bit, why do we even care about energy other than because everybody wants to talk about it? There's Tesla out there, there's, Bill Gates yesterday talked about, he's spending billions of dollars on energy storage. So it's just a hot topic that people like to talk about. But if we want to talk about mining specifically, it's anywhere between 12 to more than 30% of the total operating cost of the mine. So now if we're on a gold company, you're $1,000 an ounce, that's your production cost. That's anywhere between $120 an ounce to more than $300 an ounce. That's a very significant amount of cost. And to me, when I hear that, that's actually an opportunity because I know this is a cost that you can manage. There's a cost that you can reduce. You can do that with new technology like the flotation, which you can technically potentially reduce your cost by 50% of that operation. And so is every technology or every process unit operations in the mining process season. So when I think about innovation, I think about two things. Either we're doing things better, so we're having all these little incremental changes to meet our goals, or we're doing things differently, having a step change, new technology to take us to that next step quickly. And I'm going to talk a little bit about both, but really doing things differently. So now let's talk about energy. So energy really, this is a very simplified overview of what really energy is. There's a supply side, which is how you generate the energy you actually want to use, whether that's electricity, whether that is oil that's being refined. And then that energy is being generated, usually not right here. It needs to be moved to where you need to actually use it. And lastly, if we have a boundary of any operation, mining or this building, for example, then the energy is actually being used. That's where most of the people, when people think about energy, they think about how we use energy. And when we talk about using energy, it's the actual amount of energy that's being used to do the work. And in this case, usually there are two inefficiencies or two waste streams that can be improved upon. One is inefficiency, and the other one is waste. So an example of efficiency would be if we switch these lights to the LED this is an efficiency improvement. If we now turn off these lights because we don't need them, that's reducing that waste. So the same principle applies. They're very simple things that we can do to manage our energy. So now the same slide, I'm just going to make it a little bit more little figures on it. We've already talked about the supply opportunities. That's electricity, fuel. And as we just talked about, most of the time, energy is actually not generated on where we want to use it. And with this movement on how renewable energy and alternative energy generation opportunities coming up, there are all these people talking about, well, the sun is not shining when we want to use the energy at night. What do we do? So there's a huge conversation, a huge topic on energy storage last little while. And we'll get into that for a little bit. And same thing when it goes to the site. Sometimes the energy gets to the site needs to be stored because you may have issues with how much power can actually come to the site at the right amount and the right quality, and different things can happen. So I'm going to talk about each of these aspects. I'm going to give you some examples, and we can have a conversation on what you think of energy and what do you think of each of these aspects. So I'm going to start with the supply side. I'm going to have these little information that I just take from the internet. It knows everything that I need to know. So just an example, something that's pretty interesting to me is in 2014, 23% of the world energy production electricity production is actually from renewables. In this case, they put in hydroelectric as part of the renewable. If you take that out, it's obviously much smaller. But in North America, for example, it's about 5% of the total electricity production in 2014 is from wind and solar, and that's going to go up. In Europe, I think it's about 20%. So I'm going to talk about 3 different supply technologies. I mean, we all know about the solar PV panels and the wind turbines, small and big, so I'm not going to talk about them. So the first example I want to talk about is small-scale nuclear power plants. Normally, power plants we have are 1,000 megawatt in generation, and it's very difficult to scale them down. It requires a whole ton of water for cooling and all these other maintenance issues, and safety and waste and everything you can think about. But nuclear power is considered a clean power in terms of at the point of generation. So there has been a lot of interest on how do we utilize this nuclear power differently. So this company called NuScale Power has developed 50 megawatt scale of nuclear power plants. They can actually be shipped on a trailer like that. I don't know if they actually be able to do that in terms of safety regulations. This is not real. It's just a concept. But they have developed a 50 megawatt pilot scale or prototype that is operational. They're very small, and something that's actually really interesting in this particular example is that it's actually not very expensive. They're claiming that their cost of generating power is about $5,000 per kilowatt. I mean, it's expensive, but it's not that expensive. I'm surprised that it's actually within a scale that I can live with. So that's one example, and I just want you to keep in mind of that 50 megawatt. In mining operations, most of the time we're probably not in that power requirement. If you have let's say if you have a gold mine, that's about 5,000 to 10,000 throughput type of operation. You have a mill and let's say you have an underground mine. You're probably looking at somewhere between 15 to 25 megawatt is sort of your range of power requirements. So another example that's related to solar is what we call the concentrated solar. So instead of converting sunlight directly to electricity, these what we call concentrated solar plants are it's basically a heating system where it concentrated solar to heat up a fluid and then generate power using that hot fluid. The main benefit of that is that it can be a much, much larger scale, and it usually works really well in places where solar is available. So in this case, there's a proposed project in Chile that are looking into building a 260 megawatt plant, so much, much higher than that nuclear power plant we just talked about, and probably much, much higher than what this mine will require. In this case, they have a storage system that comes with it, which we'll talk about storage in just a couple slides. And this will provide more power than just the mine. So something that I think about when I look at these two systems, they're pretty cool. They're not extremely expensive, but it doesn't quite match in a mine that we typically want to think about. So this is where this shared economy and thinking about how can we combine these opportunities with other operations around the area. So the small-scale nuclear power plant, for example, is actually being considered in the oil sands because they have operations that are not very far from each other. They could build transmission lines to each other so that they can utilize this, and having a small-scale system, and that's able to provide power at a reliable and cheaper cost compared to if you were just to build on your own. So same thing with this project, they're going to be able to provide power to the communities. Again, both projects are not real, they're just in concepts. And the third one I want to talk about is, again, borrowing from the oil and gas industry, is waste energy. So waste energy can either be used to generate power directly through various different power cycles, or they can be used to provide heat. In this case, it's to use waste heat to preheat process requirements, and in this case, they are saving about $2 to $3 million a year based on the energy that they were able to recover. So there are lots of opportunities in mining on waste energy recovery. A lot of time, very low grade, but there could be some really good opportunities if you think about your waste mine water stream, the kind of temperature that it has, and the type of opportunity you may be able to inject that into for preheating air, for example, in the wintertime. So these are the 3 examples I want to talk about on the supply side. And if you have something specific you want to ask, or any new technologies that you thought you may want to discuss, we can talk about them now or in a bit. In a bit? Yeah. Okay, in a bit. Okay, so the next part is on energy storage, and this is like the big thing that everybody wants to talk about. I briefly mentioned Bill Gates said something yesterday, As much as, does anybody know what he said yesterday? You do.
Says energy will empower people to get out of poverty.
Yep. Okay. So he also used he discussed a formula. Did you read that whole thing? No. This is actually a very interesting. This equation is very simple. So he says the overall. He didn't develop this. He borrowed it from somewhere else. He said the overall emission of the world equals to the population times the services required per individual times energy required to provide the service per individual times the emission factor of that energy source. So in order for us to curtail our emissions, we're not going to wipe out the human population, and we're not going to not have any services. Hence, the only thing you can do is to make that last variable, which is the emission per energy source, to 0. That's the only way you can solve the problem of the world. And you can do that with the renewable energy, and therefore, the biggest challenge is on energy storage. This is what he said. So professionally, I quite disagree with some of the things he said, but I think it's important that people like himself, who are one of the richest people in the world, that are able to come out and say that, hey, this is an important thing that we should think about. And when people talk about stuff like that, it gets attention. So I'm happy with that, as much as I disagree with the actual content of that message. So here is a research that has shown that how much the energy storage market is going to grow in the next, 10 years, not even 8 years. And it's a huge number. And because every time we now generate energy, you're going to have to store it somehow. Another example I read on news yesterday was we know that the oil price is really, really low. So there's a huge market right now where companies like Glencore is buying or renting tankers so they can store fuel parked somewhere near their operations around the world. And so that business is booming right now. If you have a tanker that you can rent out, you're going to make tons of money. So that's another way of storing energy. So we have to talk about Tesla when we talk about energy storage, because that's what everybody talks about. Just an example here on sort of the scale of things here. If we want to talk about 50 kilowatt hour of storage, a typical home in North America probably use on average about 2 kilowatt, anywhere between 1 to 3 kilowatt, depending on how many things are actually running. So let's use 2 kilowatt. If you have 50 kilowatt hour of storage, that means you can use it for a day and an hour. And that's what it takes. You would need to have 100 car batteries at home. You need 5 of those Tesla power walls that they're talking about. You need some other batteries that's probably, so these batteries are probably also lithium-ion batteries. They're actually quite similar, just in different packaging, and something maybe in the future where they can have even higher energy density. So I want to bring this example out because we just talked about for mining operations, we're talking at something about 15 to 25 megawatt. So if you want to have these kind of storage for that kind of operation, it probably isn't going to be very cheap, and it's probably going to be fairly difficult to make this work. So really, I wanted to talk about energy storage in batteries, that there are many other options. Lithium-ion batteries, as much as they have high energy density, is not the only options. You really want to look at your application, your specifications, how much energy do you need right away, how long do you want to have it stored for, and at the end of the day, because energy are sort of judged by their energy density, how much space you have for the energy you want to store. So if you can get all those things figured out, then you can select one of a number of technologies that's available in the marketplace. So one example I want to talk about, which is a mining example, is American Vanadium. It's a junior company that has a project in Nevada on vanadium. So vanadium is a rare earth metal. 95% of that is being produced in China right now, like many other rare earth metal. And it's really only being used as a metal, a steel strengthener. So when you make steel, you would add a little bit of vanadium in it. It doesn't really have any other market, actually. So this company find this asset and they say, this is pretty awesome, but they can't sell the product. There's nobody who's buying the product. If they were to actually produce what they said they would flood the market by more than, 300% of whatever the current demand is. So they're looking for a market for that. And vanadium flow battery is a battery that is around for a long time, so this is not a new special technology. A flow battery typically is quite interesting because they have less parts, because they really use just one material. Most of the batteries have 2 materials. and you transfer the ion through electrochemical reaction. The flow battery usually just have one material, so it's supposedly easier to manage. And their main benefit is that it's very scalable. You can just put in a bigger tank, then you can generate more power. If you want to store power for a longer period of time, just put a bigger tank somewhere else. So in this particular case, they're talking about, well, we do have a lot of space in where we're going to mine, and they're actually hoping that they can actually generate the battery on site. So not only that they're just mining, they're also going to be processing and building these batteries right on site. And they're going to be using these batteries for their energy storage, as well as they're going to be selling these batteries. So the vanadium flow batteries are around. There are many installations around the world, mostly in remote communities for smaller scale type of remote communities on power supply. So it's a neat idea. If anybody knows this company, they're not doing very well in terms of stock price, but I think it's a really good idea, and it has its merit when the right time has come. The third example I want to talk about is it's not for the actual mining operation, but it's when the mine life has exceeded its mine life. Now you have these tailings ponds you have to manage on a regular basis. In this particular case, what they were able to do is to have what we call pump storage. So you kind of have to have the right setup for it. So you basically have an elevation change between two areas you can store water. And when the electricity cost is high, you would be releasing the water that you've just stored overnight to generate power to sell into the market that is expensive. And at night, when the power cost is low, you would be then pumping the water upstream and store them, and this process repeats on a daily basis. The downside of this compared to the previous energy storage opportunities is that, of course, you're going through a mechanical process, so the round trip efficiency is a bit lower. But in certain cases, there are pretty good business case. So this is going to be built. It is not yet being built, but 400 megawatt power plant. It's actually quite significant, and it's good for 5 hours, and therefore it will be able to provide that peak energy requirement in Ontario and in other places. There are many pump storage facilities around the world in this scale and larger. So now we talked about the supply side and the storage side. I want to talk a little bit about transmission. If we have to talk about all these things, and this is the least interesting part, I guess, in terms of talking about energy, because we don't seem to have very many options. This is just kind of a fun figure that I found recently. This is how big a tanker actually is. It's taller than the Empire State Building if you were to flip it upside down. And that holds about 2 million barrels of oil. In terms of everyday activities, it's good enough to fill 5 million cars, typical passenger cars. And that's the size of the tankers that's floating around the world. Because where energy is being produced and where energy is actually being used, this is oil, is not in the same place. So they need to be moved. And this transmission is a huge cost, and it's not really the most efficient. So one of the main advances in transmission, which nobody really talks about, and it really doesn't sound very exciting, is just how high voltage transmission lines. When you drive by these transmission lines, you can see that the lines actually sags a bit. And the higher voltage that you're transmitting, the higher the temperature gets, and the more it sags. And whenever it sags, there's lots of issues, but really also loses its effectiveness, and it's not as efficient when it does that. So there are different technologies that you can do that. Mostly the best technologies nowadays is what they call the high temperature, low sag material. So instead of having just steel surrounding your actual transmitters, you now have these composite core to make it stronger. So the composite core makes it stronger, so it does not sag as much as it normally does. It doesn't sound very exciting, but you know what? If we can actually change all the transmission lines around the world, we'll be making I don't know how much energy, a lot of energy. So the sort of the rule of thumb on how much you can save is for every 100 kilometers, you can save about 20,000 megawatt hour per year on energy. Sorry, 20,000 megawatt hour. Yeah, 20,000 megawatt hour per year. That's actually quite significant. So this is an innovation that it's been around for a while. It's finally getting into implementation. It's very difficult to convince companies to do this sometimes because we always like to go for the lowest cost. But if we can do this, it's going to have huge impact in the world on energy supply and transmission. The other thing about energy transmission is, I don't know if you read about this, but that people are now starting to look at airships to move material, fuel, and people to remote mine sites, and how this is a more efficient way of doing things. And it moves pretty fast, and it basically takes a much larger volume than what you could have done normally with current opportunities in very remote areas. So that's pretty cool. So now that's the transmission side. So lastly, I want to talk about the demand side. There's 4 examples I want to talk about. So this is where we actually use the energy, and how can we be more efficient and effective and doing things differently on the user side of things. Globally, we've actually done well in terms of reducing our energy intensity per person. So we've done this over the year. But that doesn't mean that, it's a numerator denominator math, right? So we also have more people today. So overall we have increased our energy consumption quite significantly, but we've also increased our population significantly. So that number is interesting to look at. What does that really mean? It's difficult to say. So one example I want to talk about, and I think in mining, especially for underground mining, we talk about air quality, we talk about diesel particulate matter, we talk about ventilation all the time. And one of the ways to really change that is to go into using an electric fleet. If you can electrify your underground completely, then you don't have these air quality issues. You don't have the ventilation requirements that you were supposed to have. And it will really change how the energy footprint as well as operational footprint quite significantly. So in Northern Ontario at Curtin Lake Gold Mine, they're the only company, the only mining company in the world, I think, that has a sizable fleet of underground electric equipment. Many other mines are piloting 1 or 2 or 3 main carriers, maybe a scoop here and there, but they've got a fleet of 15 underground equipment, including scoops and trucks. They have 20-ton trucks and 3.5-yard scoops, and they're going to be adding more this year. What they've done, and they've done lots of things. If you're interested in electrification of your fleet, certainly get in touch with them. They'll probably be happy to give you a tour. One of the main challenges they got is, of course, once you get in, you can't get out. You gotta do it the whole way. So you can see that even though they have all this equipment, they have 15 equipments, but they probably have 45 batteries, because each equipment probably needs more than 1 battery a day. It takes 8 hours to charge. It runs for 8 hours. And so they have this huge underground electrical infrastructure now that they have to maintain, which is actually pretty cool. So they've gone down the road. People are very happy with the success, and I know that a lot of mining companies are now piloting and looking into new underground electric fleet. So another example on the sort of moving things a bit differently is this company called ETF. They basically have these modular design of the chassis of the truck. So you can put any kind of engine on it. If you want to have a natural gas engine, sure, go for it. If you want to go have a diesel engine, you can put it on. They can design everything basically modular using existing technologies. And they put it together, they do all the engineering, and then they would allow you to move material a bit differently. Some of the things that they're also doing is you can actually connect these trucks to each other, so they become sort of like a hollow train, which reduces the power requirements, and they can be releasing the material from the side instead of from the back. So there's a lot of different things they're doing here. So just different way of doing things. It's really same, we got a hull, so what do we do differently to do it? And this is my favorite example that I want to talk about today. It's on 3D printing. So 3D printing is something that we talked about, and most of the time on the consumer side, we hear about how you can print, I don't know, a little gadget, a little earring, or something to put your cell phone on your desk. But really, the technology has improved very significantly. And nowadays, we are actually doing 3D printing on a lot of the aerospace materials. Not all the structural stuff at the moment, but the hinge on your table tray, or the luggage room and luggage space parts. A lot of them are actually being 3D printed. There are many reasons why that's beneficial. For aerospace, for example, it really reduces the cost. It reduces the weight of these components. And that's what affects the efficiency significantly. But really, if you can have them on site when the technology is there, you could be printing a lot of the materials on site and custom to your design. And you can really improve your availability of your equipment, managing those downtime a little bit different, and preventative maintenance a little bit differently, and be able to improve upon that. So that car there is the first 3D printed car in the world. I think this is last year, I think. It's got to be 2015, yeah. I don't really know if it passes all the safeties, but you know, the message the message is that it's possible. We're not just printing the little gadgets that we're going to put on our desk anymore. It is possible. And this engine here is a GE product. They're doing 3D printing of jet engines. So you know, it's happening.
That's not this big.
It's real. Well, yeah, they didn't have a person in it. Yeah, but yeah. So the company is doing. I mean, they've got some VC funding, so they are doing it. I'm pretty sure that's a real size. But anyways, so the last thing I want to talk about is really on the data side of things. You know, we talked about some of the innovation we can do is with all this data that's available to us. You know, we talk about this individual different kind of systems, but for any of the systems to really come into play and having the right information and feedback and control, we want to be working with that information a little bit. I don't want to get into details, but if we have time, we can talk about a whole entire presentation on just how technology on data, big data has changed mining and will change mining. So these are all sort of just little pockets of different things on different side of things, on the supply, on the storage, on the transmission, and on the demand. I know that I didn't have very much time, so I didn't want to get into too much detail of any of these items, but I'm certainly happy to discuss further. The last message I want to say is, you know, in each of this sector, there's tons of opportunity for innovation, both on that incremental changes, doing things a little bit better, putting that variable speed drive that you want, upgrading to more efficient equipment, to these step change opportunities like a new flotation system. So we have a lot of opportunities, and we can certainly reach those goals. So that's all I have. Now I'm happy to have a chat on whatever you have in mind.
Thank you.